Hi, I am ARIFATUL. So, I'm going to explain question number 1, which is describe the difference between groups and ring. For groups, a group is a finite or infinite set of elements together with a binary structure, where G is a non-empty set and multiplication is a binary operation on G, such that the following axioms are satisfied, which is closure, associative, identity, and inverse. The inverse should be unique. While for rings, a ring is an algebraic structure consisting of a set together with two binary operations usually called addition and multiplication, where the set G is an abelian group under addition and a monoid under multiplication such that multiplication distributes over addition. A ring R is a set with laws of addition and multiplication such that R is an abelian group under addition satisfying the following condition, which is additive associative, additive commutative, additive identity, additive inverse, and multiplication is associative, also distributive laws, which is left distributive and right distributive. For properties for groups, the first one is left and right cancellation law. If G is a group with binary operation, then the left and right cancellation law hold in G, that is, A times B equals to A times C implies B equals to C, and B times A equals to C times A implies B equals to C for all A, B, C in G. This is the example. The next properties is unique solution. If G is a group with binary operation, and if A and E are any element of G, then the linear equation F times E equals to H and G times E equals to H have unique solution A and B in G. The example is this one. And lastly, we could conclude that the uniqueness of G follow similarly because this F1 is equal to F2. The next properties, the uniqueness of identity and inverse element in G. In a group G with binary operation, there is only one element E in G such that A times E equals to E times A equals to A for all A in G, while for each A element in G there is only A prime element in G such that A prime times A equals to A times A prime equals to A. Therefore, the identity and the inverse of each element are unique in a group. This is the example for properties of the uniqueness and inverse element in G. Lastly, the inverse of B in group G is unique. While properties of ring, the first theorem, which is multiplication rule, this is the properties and this is the example. Next, these properties and this is the example. While then for the third properties is this one and this is the example to prove the properties. For theorem 2, which is uniqueness of the unity and the inverse, the property said that if a ring has a unity, then it is unique. So this is the example to prove the following properties. The second property is if a ring element has a multiplicative inverse, it is unique. Then the example is this one. So lastly, since B equals to C, then the multiplicative inverse is unique. That's all. Thank you.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Nurfarhanah Binti Salleh. I am studying in Group C, SMA3033 Algebraic Structure. So this video presentation is for my assignment 2 and I am doing question number 1, Roman 3. The question is about the overall description of the differences based on the two facts above and the relationship between the groups and the rings. So I have divided the differences into three parts, which is in terms of definition, in terms of properties, and overall summarization of the differences. So firstly, I'm going to start with the differences of groups and rings based on their definition. So, the definition of groups: a group is a finite or infinite set of elements together with a binary structure star, where G is a non-empty set and star is a binary operation on G such that the following axioms are satisfied, which is closure, G1 associative, G2 identity E, and G3 inverse. So, for ring, a ring R is a set with laws of addition and multiplication such that R is an abelian group under addition satisfying the following conditions, which is additive associative, additive commutative, additive identity, additive inverse, multiplication is associative, and distributive law. Next, the differences of groups and rings based on their properties. I have divided it into 5 properties. Firstly, for left and right cancellation law, if G is a group with binary operation star, then the left and right cancellation laws hold in G, that is A star B is equals to A star C implies B is equals to C. And for rings, there is no left and right cancellation law. For unique solution, if G is a group with binary operation star and if AB is element of G, then the linear equation A star x is equals to B and Y star A is equals to B have unique solutions x and y in G. So for rings, the solution is not necessarily unique. For uniqueness of identity element, in a group G with binary operation star, there is only one element, E element of G, such that E star A is equals to A star E is equals to A for all A in G. For ring, if a ring has unity, then it is unique. Next, for uniqueness of inverse, in a group G with binary operation star, for each A element of G, there is only one element, A prime element of G, such that A prime star A is equals to A star A prime is equals to E. For ring, if a ring element has a multiplicative inverse, it is unique. So, for rules of multiplication, there are no specific rules for multiplication in groups. There are 4 rules for multiplication in rings. Next, we will look at the overall summarization of the differences. I have divided it into 5 different elements. Firstly, for binary operations, group have only one binary operation, whereas rings have 2 binary operations, which is addition and multiplication. For identity in groups known as identity element. If a ring has identity, it is known as ring with unity. For inverse in groups known as inverse element, inverse in rings with binary operation multiplication known as multiplicative inverse. If a ring has multiplicative inverse, it is known as unit. So for commutative, if a group is commutative, then the group is an abelian group. If a ring with binary operation addition, it is similar to abelian group, but ring with binary operation multiplication, it is known as commutative ring. In terms of properties, there are 3 properties that can be applied in groups, and there are 2 properties that can be applied in rings. So that's all with my presentation. Thank you.
Good day all. First of all, I would like to introduce myself. My name is Shanthene and I'm from Group C. Well, today we will look into some of the questions regarding algebraic structures, or more known as abstract algebra, and we would like to learn about some of the components in abstract algebra. First of all, what is a field? So the definition of a field is a set with two binary operations of addition and multiplication, where both of which operations are commutative, associative, contain identity elements, and contain inverse elements. So the identity element for addition, we all know that it is 0, and for multiplication, it is 1. If given x, the inverse element for addition is negative x, whereas for the multiplicative inverse element for multiplication is 1 over x, but remember that x must not be equivalent to 0. Furthermore, we must also remember that multiplication distributes over addition. One example of the field of rational number q, that is all numbers q such that for integers a and b, q is equivalent to a, b, where b is never equivalent to 0. The definition of a field applies to this number set. We also note that the set of real numbers R is also a field. Since Q is a subset of R, the rational numbers are subset of the real numbers. So we can say that R is a subfield of R. Alternatively, we can also say that R is an extension of R. So a further example to justify why R is a field. Okay, we suppose that A, B, C, and D element of R. We know that R has addition and multiplication as binary operations, since A plus B equivalent to C for some C, and AB equivalent to D for some D. Furthermore, we know that addition and multiplication defined on real numbers is both commutative and associative. Besides that, the identity element for addition is 0, since for all x element of R, which is real number, x plus 0 is equivalent to x, and the identity element for multiplication is 1, since 1x is equivalent to x. Lastly, the inverse element for addition is negative x, since x plus negative x equivalent to 0, where 0 is being the identity for the addition. And the inverse element for multiplication 1 over x, since x times 1 over x is 1, where x is never equivalent to 0. Moving on to the next question. Question 3.
So a very good morning. I would like to greet to everybody. So today I'll be presenting assignment question number 2 Roman 2 and number 2 Roman 3. So let's move. The first question is question 2. The one I'm going to present will be what is an integral domain. So the first definition, there is two different type of definitions. The first definition is for zero divisors. So the zero divisors are non-zero element of a commutative ring R such that there are non-zero element B in R, such that when A times C is equals to 0. So for the next definition will be integral domain. So integral domain is a commutative ring with identity and non-zero divisors. So there is one theorem. The theorem is called cancellation. So to prove that theorem, I have done this very simple proving. So AB is equals to AC. So we bring AB and AC to the left hand side. We factorize it and you will get A bracket B minus C equals to 0. So integral domain A is a set of two binary operations called addition and multiplication, which have the following properties. There are few properties. So the first one will be closed under addition, to show associative under addition, additive identity 0 exists under addition. Addition inverse exists under every element under addition. Commutative law closed under multiplication. Associative law identity element 1 exists under multiplication. Commutative law holds under multiplication. Left distributive law, right distributive law, and non-proper zeros, properties of zeros. So next we move to question number 2, Roman 3. What are the relationship between a field and an integral domain? So basically there are few theorems in this. So I'm going to point two theorems. So the first theorem will be a finite integral domain D is a field. So to prove this, I have listed out a few steps. So here, let's consider, let's say A is in B, which is the ring. A is not equal to 0. If A equals to 1, then A inverse is equals to 1 as well, and A is a unit. Suppose A is not equals to 1. Since D is finite, so each element in I, J is included in n natural numbers with I minus J is more than 1. So by cancellation law, so what I've done here is I've brought both AI and AJ to one side, factorized it, subtracted it. So I'll get this final answer will be AI minus AJ is equals to 0. So as A is a non-zero and R is an integral domain, so AI is non-zero, then 1 minus A, I minus J equals to 0. It follows that as A j minus I is minus 1 is equals to A equals to 1. Next will be proposition 2.14. Every division ring is a domain. So every field is an integral domain. Here I've done a very simple explanation, very simple proof. So here let R be a division ring, and suppose Rs is in R with R multiplied by S is equal to 0. Assume R is not equals to 1, then R inverse exists and 0 is equals to R negative Rs. This example is actually I'm showing I'm showing the usage of group. So the first one is what I did. I used group 3, which is R inverse. I did using group 3. The second procedure is I use R2, G2 group 2, and lastly identity S. So whatever terms with identity, you will get S. So therefore R contains no division of 0. So that's all from me. Thank you.
Moving on to the next question. Question 3. Consider the set of matrix of 2 by 2 matrices over the integer with operations addition and multiplication. First of all, we have to find for part 1 whether or not the matrix is a commutative ring. So, for the first part, we have to prove that addition and multiplication is a binary operation on the matrix over the integer. So we let a matrix A such that ABCD is an element of the matrix over the integer, where ABCD is an element of set, and we let matrix B, E, F, G, H, element of the matrix over the integer such that E, F, G, H are elements of set. So we need to show that A plus B is an element of matrices over the integer. So when we compute the following, we will have addition as the binary operation on matrices over the integer. Next, we have to show that AB is an element of the matrices over the integer for multiplication. So matrix A times matrix B, we will have this matrix here, which is an element of matrix over the integer, where all the elements in this matrix is also the element of the integer. Therefore, we can conclude that multiplication is a binary operation on matrix over the integer. The second part of the proof is to show that the addition and multiplication is associative on matrix over the integer. So here we let 3 matrices A, ABCD, B, EFGH, and C, I, J, K, L. And all the elements inside all these matrices are elements of the integer. First, we show the associative for the addition property, where A plus B plus C is equivalent to A plus B plus C. The left-hand side has to be equivalent to the right-hand side here. So when we add, we solve A plus B first, and then we add them with the matrix C. So we will have this matrix where we can conclude that the left-hand side is also equivalent to the right-hand side because addition is associative on the matrix over the integer. So we can conclude here that addition is associative on the matrix 2 by 2 of the integer. Next, we also show that the matrices are associative in multiplication. So here also again we prove the left hand side equals to the right hand side. So when we multiply matrix A times B and then we multiply the answer with matrix C, we will have the following matrix here. So here we can say that multiplication is associative on matrix over the integer, and then we can conclude that left hand side is equivalent to the right hand side. So we can say that multiplication is associative on the 2 by 2 matrix. The third proving is to show that addition is commutative on the matrix 2 by 2. So we let a matrix A equals to A, B, C, D, where all these elements are elements of Z, and a matrix B, E, F, G, H, where all the elements are elements of the integer as well. So to show commutative, we have to show that A plus B equals to B plus A. So for the left hand side, when we add matrix A with matrix B, we will have this matrix here. EF GH plus ABCD. Here we can conclude that the addition is commutative on the matrix 2 by 2. So the left hand side is obviously equivalent to the right hand side, and we can say that addition is commutative on the matrix integer. The fourth proof here to show that the matrix is a ring is to show the additive identity or 0 exists. So we let a matrix A, element of matrix 2 by 2 over the integer, where all the elements are element of Z, and same thing goes to the matrix B. We let another matrix B, E, F, G, H, element of the 2 by 2 matrix, where all the elements in the 2 by 2 matrix are elements of the integers as well. And we let this element B, the matrix B, as the identity element of the 2 by 2 matrix. So here we would like to show that A plus B is equivalent to the A, and B plus A is also equivalent to the A. So here our matrix B behaves as the identity matrix. So when we compute the left hand side, A plus B equals to A, we are going to get matrix B, which is equivalent to E, F, G, H, equals to 0, 0, 0, and 0, where all these elements are elements of the integer. Same thing goes to the right hand side when we compute B plus A equals to A. So we will have E, F, G, H equals to 0, 0, 0, 0, where all the elements are elements of the integer as well. So since LHS, where the left hand side is equivalent to the right hand side, so we can conclude that the element 0, 0, 0, 0 is the identity of matrix 2 by 2. So the fifth proof to show the additive inverse exists. So here we let element A, matrix A, equivalent to A, B, C, D, where all the elements are elements of the integers, and let B, E, F, G, H where all the elements are again the elements of the integer. So here we let B, matrix B, as the inverse element of the 2 by 2 matrix. And we also let E equals to 0, 0, 0, 0 as a 2 by 2 matrix identity. So here we want to show that A plus B equals to identity E, and same thing goes to B plus A equals to E. So for the left hand side, when we compute, we will be left with the inverse element of negative A, negative B, negative C, negative D. All those elements in this inverse matrix are elements of the integer. As for the right hand side, when we compute B plus A equivalent to E, and we have also again the inverse matrix as negative A, negative B, negative C, and negative D. All these elements again are elements of the integer. So since left hand side is equivalent to right hand side, we can conclude that this element is the additive inverse of the 2 by 2 matrix. Now, to show that multiplication distributes over addition on the left hand side and right hand side. So here we let 3 matrix, which is matrix A, B, and C. So here we want to show that A multiplied by B times C is equivalent to B plus C multiplied by A. When we compute the left hand side, we are left with this matrix here. And when we compute the right hand side, we are left with the same. We are left with this matrix here. And this matrix, this both left hand side and the right hand side, are pretty much the same. So we can conclude that the left hand side and the right hand side are equal. So we can conclude that multiplication and addition distribute. As for the seventh part of the proof, to show that the multiplication is not commutative on the 2 by 2 matrix. So here we take a counter example where we let matrix A equals to 1, 2, 3, 4, and we let matrix B equals to 5, 6, 7, 8. So here we want to show that matrix A times B is equivalent to B times A. So since our left hand side is not equivalent to right hand side when we compute, so we can say that multiplication is not commutative on 2 by 2 matrix. Thus, based on proof 1 to 6, we can conclude that 2 by 2 matrix is a ring, but not a commutative ring based on proof 7. As for the second part, the question asks us, does the 2 by 2 matrix over the integer has a unity? So how can we justify our answer here? So we let a matrix A equals to A, B, C, D, and this matrix A, B, C, D we multiply by another matrix, say 1, 0, 0, 1 equals to A, B, C, D. And again, on the right hand side, we have the 1, 0, 0, 1 matrix multiplied by A, B, C, D matrix. So it is also again to A, B, C, D. Therefore, we can conclude that the 2 by 2 matrix has the 1, 0, 0, 1 as the identity element. Thus, we can conclude that the ring, which is the 2 by 2 matrix over the integer, has a unity. And that's all from me for now. Thank you.